Okay, so this week mainly we are going to discuss logistic regression, which is a very interesting topic. What is logistic regression? So basically, it extends the idea of linear regression to situations where your outcome variable is categorical or a factor type of variable. So far in linear regression, simple linear regression, and multiple linear regression, we had a response which was mostly numeric. So either numeric or it could be continuous variable. But if you have a response, it doesn't matter what you have for your independent variables. Independent variables can be like numeric, it can be factor or mix of them. But the method changes or need for logistic regression only comes when your response is a factor variable or a categorical variable. So that's why outcome decides which method is applicable, not the independent variables. So some examples: classifying customers as churn or not churn. So this term churn comes from telecommunications business, and let's say a customer has some kind of agreement with AT&T for 2 years, but after like 2 years they are free to go to somebody else. They can go to Verizon or T-Mobile or anywhere. So if a customer leaves, so that's called churn. And you can imagine a company like $200 billion company with a $200 million market cap, even 5% customers churn, that's a huge loss. So studying churn is very, very important for many businesses. Nobody wants to lose customers, and especially after keeping them for some time, because it's very difficult to get a customer. Lot of efforts, marketing, ads, all those things are needed. And then when that customer leaves, that's a big loss to the company. So there could be problems where classifying customer as churn or not churn, because if you can develop a model and accurately predict which customers are likely to churn, and then instead of targeting like blindly left and right everywhere, sending brochures or marketing material, if you focus on those maybe 100, 200, 500, those are likely to churn, you can reduce your budget significantly and save a lot of money every year, because many customers may not be thinking of churning, and you are bombarding with like a lot of material, and each marketing material may be costing a lot of money. So you can save, as a companies can save a lot of money. So that's why they focus on this. And not only businesses, but even for academic institutes. In fact, there is a data, I'm talking about like undergrad students who enroll in a undergrad program, and they study at a university during first year. And what happens is the university, this is across US, is able to retain approximately on only like 70-75% of those students. So lot of students, they churn means they leave, and they maybe they have plans to go to some other universities even before, because there is a friend or because a better program. But that also is a big problem for businesses, like 30% or 25% customers churning. That's going to be a huge thing. Another example is classify student applications as admit or reject. So especially in popular programs, when applications are invited, and especially when the programs are popular, a lot of students apply to good schools, and maybe there are only x number of seats, and number of applications maybe sometimes much more than that. And every university You go to every department you go to, you'll always find that they have limited resources, meaning limited number of people to really address things. So in those situations, some kind of model, if it is available, that can help to classify those applicants very quickly, maybe into three categories, I would say, like admit, reject, and something which is in between, which cannot be decided by a program or a model or a computer or a machine, but where human intervention is needed. So only there you use your manpower or people who work on it. But other things can be automated in some way, and applications can be quickly decided on. So there also logistic regression could be a good model to use. Another example where outcome or the response variable or the y variable is factor or categorical is when we develop models to classify a patient to have cancer or the person is healthy. So again, two categories based on past data, a model can be developed that can quickly help to decide. One more example I have listed here is classify a customer as will accept credit card offer or will not accept credit card offer. So these are like very common areas of interest. So let me talk about logistic regression a little bit more. It's a special case of generalized linear models, GLMs, and among GLMs, logistic regression is very popular. In fact, I have seen a research paper where I found that of all the classification problems involving some kind of statistical or machine learning applications, 80% of the problems are such where you are you are trying to classify or trying to develop a model that can classify response into one of the two categories. So there are a lot of applications of such classification. For GLM, we do not assume linear relationship between dependent and independent variable, because your dependent variable here is not a numeric or continuous variable. So typically the concept of correlation between two variables is most suited to continuous variables or numeric variables. But when you have your response as a categorical or a factor variable, so obviously we have to get rid of that assumption. It allows for non-normal error terms. So remember, in multiple linear regression and simple linear regression, one of the assumptions was that the error terms are normally distributed with mean zero and variance sigma square. But here it allows for, so the model or approach that we use allow for non-normal error terms. Another major difference is logistic regression uses maximum likelihood estimation, MLEs, instead of ordinary least square, OLS, that we have been using so far. So maximum likelihood, in fact, is a general method, and this OLS or ordinary least squares is a special case of MLE. For linear regression situation, it's a special case. So some of the differences that you see or you'll notice, we still talk about degrees of freedom in both, whether it's regression or logistic regression. In linear regression, we talk about sum of squares, but in logistic regression, we talk about deviance. So when you see the outcome, when you see the summary of the model, you'll notice that we do not have sum of squares there, but deviance. Mean sum of squares divided by degrees of freedom. So that's sum of squares divided by degrees of freedom. And a similar concept in logistic regression is mean deviance. So we divide d or deviance by its degrees of freedom to get mean deviance. In linear regression, we fit models by minimizing the residual sum of squares. So we try to find b0 and b1 in such a way that we minimize the squared errors around that line. Similarly, in logistic regression, we fit models by minimizing the deviance. So we try to estimate b0s and b1s in such a way, let's say your response is either 0 or 1. So a customer churns or customer does not churn. So churn could be 1 and doesn't churn could be 0. And if you have 5,000 data points, so you have 5,000, like if you add like how many zeros and how many ones, you'll have 5,000 zeros and ones. And the way logistic regression tries to estimate b0 and b1 using MLE's maximum likelihood estimation is that it tries to find a way so that when the answer is 1, it should be very close to 1. And if the answer or response is 0, it should be very close to 0. So it will try to do that for each and every case. New term that you may hear with logistic regression is called the Logit. So here the goal is to find a function of the predictor variables, your x1, x2, x3, and so on, independent variables basically, that relates them to 0 or 1 outcome. Instead of y as an outcome variable, which we do in linear regression or multiple linear regression, so instead of using y, because now your y is a categorical or a factor variable, so we cannot use y as it is, but we use a function of y, and that's what is called logit. Now, logit can be modeled as a linear function of the predictors. So your logic may be equal to b0 plus b1x1 plus b2x2 plus b3x3 and so on. So it can be modeled as a linear function of the predictors. So the right side of the equation that you have seen in multiple linear regression is exactly same format, b0 plus b1x1 plus b2x2 plus b3x3 up to maybe bn xn. What changes here is instead of y on the left hand side, you have logit. So that's a major difference. The logit can be mapped back to a probability, which in turn can be mapped to a class. So for example, if you are developing a model to predict whether a customer will churn or not churn, leave the company or will not leave the company. So using logit, we can find out what is the probability that a customer will leave the company. So unlike multiple linear regression, for example, if you are predicting or estimating house price, so what will be the house price in Boston area given like so many predictor variables. So instead of that, because now it is 0 and 1, we try to find out or map it back to some kind of probability which everybody understands and can use very easily. So if I make a table and say that these are the customers who are very likely to churn because the probability of their churning is more than 0.95 or 0.90, and this is the list of those 1000 customers. So that can be used in some way by the company to address the problem. So logit can be mapped back to a probability, which in turn can be mapped to a class. So very simple. If the probability that a customer will churn is 90% or zero point 0.9, that means that customer belongs to category 1 if the 1 here represents customers who churn. Similarly, if we find a probability that a customer is going to churn is very low, only 2%, 0.02, so that means the class is going to be 0. So the customer is not going to churn. Probability can be again mapped to a class. So what is logit? What is this thing in logistic regression? So logit is basically log odds. So instead of y, we are using this logit. But if you notice on the right side, we have exactly same format that we have for multiple linear regression. So there is no change at all. Now, what is odds? So let's say this P is the probability that something happens or probability of an event, like probability that a customer will churn. So if we denote that by P, then automatically 1 minus P means probability that that event is not going to happen. So the probability that the customer is not likely to churn. So that's called odds. That P divided by 1 minus P, the probability that customer will churn divided by probability of not churning. So that's what is called odds. Odds is something very popular. I don't know if any one of you have interest in like horse racing. So in horse racing, odds chances of like or odds of a horse winning is high or low. So that's a very common language in horse racing. So if you look at this log odds carefully, you will find that log odds is likely to range between negative infinity to positive infinity. There is no upper or lower limit it can go to. It can go to infinity in either direction. And a very low value, like a very highly negative value, essentially means very low odds, or low chance of something happening. And very high value, positive value, indicates very high odds of an event happening. If you consider midpoint for the probability like 0.5, and if you replace p's by 0.5, so 0.5 divided by 1 minus 0.5, so that means odds equal 1. And if you put that in log odds, so log of 1 is 0. So this midpoint between this negative infinity and positive infinity will be when p equals 0.5. Now this equation can be easily rearranged, and you can calculate what is called probability of an event happening. So odds can be very easily converted into or rearranged into probability. So let me use this equation and do some steps. Log of, so I'm assuming natural logarithm, p divided by 1 minus p is equal to beta 0 plus beta 1 x1 and so on to beta q x q. We have q predictors. Now suppose this right hand side, suppose we call it just y. So log of p divided by 1 minus p equals y. And if you take exponential on both sides, we'll have p divided by 1 minus p equals e raised to y. So this thing I want to solve for p. I can take reciprocal of both sides. So it becomes 1 minus p by p, and then on the right side 1 by e raised to y. So 1 minus p by p is 1 by p minus 1 equals 1 over ey. And then when we take that negative 1 on the other side, we get 1 plus 1 by ey, which is also 1 plus ey divided by e raised to y. And then you take reciprocal and you get p. So this is how probability for any data point can be arrived at. Once we have equation for or estimates of beta 0, beta 1 and beta q, so we can replace them, and for each case we have values of x1, x2 and so on. So using that we can calculate y, and then we can calculate p. So instead of talking in terms of log odds, we can always talk in terms of probability. Probability that a customer is going to leave, or probability that a student application will be accepted, or probability that a customer will accept a credit card offer and so on. So P is always easier to work with. So because of the nature of our left hand side in the equation, which is slightly different, which is Logit. So because of that, interpretation is slightly different compared to multiple linear regression situation. So for predictive classification, we typically use probability with a cutoff value. We cannot simply use P to decide a class. We also need a cutoff. When do we say a customer is likely to churn? Should it be when probability is more than 50%, more than 60%, or even more than 40%? So that percentage that we use is basically cutoff value, and sometimes it may not be, it need not be zero point 0.5. So there are many cases where 0.5 may not be the best cutoff, but usually 0.5 may work well. For explanatory purposes, odds have a useful interpretation. If we increase x1 by 1 unit, same language that we use for multiple linear regression, so x1 by 1 unit, holding everything else constant, then b1 is the factor by which the odds of belonging to class 1 increases. We are assuming that when we talk of p or probability, so it is the probability that we are talking about class 1. It is the probability that we are talking about a student getting admitted or a customer leaving a company. So we are going to look at this example of student applications where the goal is to classify student applications as admit or reject. So these students are applying actually to a graduate program, and they have undergrad degrees, and they have like data on their GPA, and I think GRE is required and so on. So that's the situation. Target or dependent variable is admit. If the student was not admitted, the value is 0, and if the student was admitted, value is 1. And these are x1, x2, x3. So 3 different independent variables. So the idea is to develop a classification model, and Later on, probably, if that model is good, then probably use that model to make your decisions quicker or faster. So when we run logistic regression model, the output that you get is familiar. Is familiar to what we have seen for multiple linear regression also. So you'll have basically intercept, GRE, all those variables. One difference you will see is that you'll see is here we are using z value or normal distribution rather than t distribution. So we are estimating these coefficients using MLEs, maximum likelihood estimator, and the z value is now based on normal distribution, standard normal distribution with mean 0 and sigma 1. And other things are familiar. We have estimate standard error. So this is column 1, this is column 2, this is column 3, and column 3 is always column 1 divided by column 2. So these z values are nothing but estimate divided by their standard errors. And based on that, in this case, using standard normal distribution, it's very straightforward to get values of probability or p values. I'm going to show this in RStudio. So let's switch gears and go to RStudio. So if you are using RStudio Cloud to read this CSV file, binary.csv, you will have to first upload it from this fourth window. Because currently, if you click on files, we don't have binary.csv listed as one of the files. But uploading this file is very straightforward. If you click on upload, I'll have to browse actually because it's on my computer. So binary.csv, and then okay. It's a small file, 5.4 kilobytes, not very difficult to get. It won't take much time. I know many of you have mentioned that you're not using RStudio Cloud, but you are using RStudio on your computer. So if you want to read this file, if it is on your computer, you can do this. So my data read.csv. If you directly say within quotes binary.csv, it may not pick up that file because binary.csv may not be in your default directory. If you want to check current working directory, you can type get wd, get working directory. You see, because I'm using this cloud platform, so it's by default, it's cloud project. So that's why I'm able to run this line without any extra information. But if you are doing on your computer, an easier way will be file.choose, open close parenthesis, comma, header equals capital T for true. So when you run this line on your desktop version of RStudio, a window will pop up and then you can locate your CSV file and just read it. But this is going to go to my data. So this is the name given by us. So if you run this, immediately you can see in the third window, my data has been read. It has 400 observations and 4 variables. So not a very huge data set. If you click on my data, it will also show you the entire data. So first column is admit, whether a student is admitted or not based on the application. 0 means not admitted, 1 means admitted. And then second column is GRE scores. Then you have GPAs and rank of the institute from where they are coming. Because this GPA of 3, for example, from a rank 1 school versus GPA of 3 from rank 4 school may be very different. So sometimes people also look at, when accepting applications, where this student is coming from. So, okay, once you read the data, it's always a good idea to look at the structure of the data and make sure that the data is in format that you want. So right now, our outcome variable admit is being shown as an integer variable because R or R Studio only sees zeros and ones and thinks that it is an integer variable. But we know that it's a factor variable. So what we need to do is we can convert this into factor by using as dot factor. If you look at structure again, now admit is a factor variable. GRE and GPA as integer or numeric, that's fine. But rank of the school from where they're applying, there are only 4 values like 1, 2, 3, 4. And it's certainly not a numeric or integer type of variable because it's also a factor variable. My data $sign rank. So if you check your structure of my data now, so it looks the way we want the data structure to be. Even before we develop a prediction model, sometimes out of curiosity, we want to know how many students were really admitted. So out of 400 applicants, how many were accepted? Somebody has 127. I'll also use table my data $sign 127. Even if you do summary my data, that can tell you how many zeros and how many ones. And among the applicants, there was 61 applying based on rank 1 schools, 151 coming from rank 2, 121 rank 3, 67 rank 4. And GRE scores vary a lot, 220 to 800, with the mean and median very close, about 580. And GPA 2.26, very low. So we have seen this in last class also. We can split the data. It's always a good idea to split the data. And let's do 80-20. We want to use 80% for building the model and 20% of the data for checking. If you use same set.seed as what I'm using, 1, 2, 3, 4, so all of us will have exactly same training data and exactly same test data. So your training data should have 325 observations and test data 75. If I do summary train, so we have good amount of data for both zeros and ones. What about test? So now we are ready to make a model, logistic regression model. So this time we will not use LM that we have been using, but we are going to use generalized linear models now, GLM, and admit as our y variable. And I'm putting a dot here, which means all independent variables should be included. And then we are saying data is train, but we have to specify that we are using binomial situation. Whenever you have response in only 2 categories, so that means we are using binomial situation. So yes, no, good, bad, churn, not churn, admitted, not admitted, accepted, rejected. So all those like situations where there are only 2 categories fall under binomial. You run this, it will automatically do maximum likelihood estimation. So when you run the summary, that will give you this output. This is the deviance, residuals, and then your coefficients. So this is what you saw on the PowerPoint. So note that in this output you will not get R square. R square is a concept only for simple linear regression or multiple linear regression situation. But when your response is factor, then we may depend on AIC and some other metrics that I'm going to show you very soon. So as far as this model is concerned, we try to minimize AIC. Other thing you'll notice is GRE is not statistically significant, but GPA is statistically significant. It has 2 stars, and rank has 4 different levels. It's a factor variable with 4 different levels. So whenever we have n levels for a factor variable, we need n minus 1 dummy variables. So that's why for rank you'll see 1, 2, and 3. Some of you may wonder, this is not statistically significant. There's no star for rank 2. Can we drop? So for factor variables, the answer in this case will be no. We cannot drop this because rank is just one variable. And if any of these dummy variables is significant, we cannot drop that variable because we cannot drop just one level of it and work with remaining. So either we are working with rank or we are not working with rank. We can drop rank only if all these 3 were not statistically significant. So in this case, we cannot drop rank. The only thing that we drop is GRE, and we can do minus GRE and run the model again. Look at the summary again. So not a very huge difference between the two situations, but at least we are not unnecessarily carrying a variable which is not statistically significant. And this becomes our, in a way, so far, our final logistic regression model. So we got this model, and then this model can be used for making predictions. And making predictions using model is not very difficult. We use a predict command, a function. Our model is M, and if you want to make prediction for the training data, so we can type, let's say, response. Let's see what we get. Instead of everything, let me say head P1. So you will notice that the response is in probability format. And if you look at head train, so in the training data, first student was not admitted. So if the model is doing well, that means the probability of accepting that applicant should be low. And based on the model, we get about 0.28. So if we use a cutoff of 0.5, anything less than 50%, we call it 0. Anything more than 50% in probability, we call it 1 for the response. Then the first prediction is correct. But if you look at second prediction, the model says, logistic regression model says, the probability of this student getting admitted is 0.29, not very different from the first one. But in fact, this student was admitted. This student came from rank 3 like the first one and had a similar GPA 3.61 versus 3.67. We had dropped GRE because GRE was not statistically significant, but this student had much higher GRE score than first one. But our model doesn't know that. Our model doesn't include GRE. So our model rejects it, but in reality, this student was admitted. Third one, you see 0.68, 68% chance of getting admitted, which is more than 50%. And in fact, this student was admitted. This is a student from rank 1 school and GPA is 4. So no doubt there's no way this student can be rejected. Applicant number 4 was admitted, but the model actually gives among first 6 candidates in the training data, the model gives very low probability, only 12%, because the model sees this student is coming from rank 4 school and has a GPA of 3.19 only, but actually this student was admitted. So you can see there are some correct classifications, there are some incorrect classifications. No model is going to be 100% accurate, but usually we want to develop a model that will do a better job. So basically what I did was I looked at the RStudio output and then I replaced B0, B1 and so on, so that this becomes our logistic regression model based on the data training data set that we used. So how to use this? Let's say we have a new applicant who comes from rank 1 school and had an undergrad GPA of 4. How do we use this model? So let's say we want to find what is the probability that this student will be admitted. So remember this equation that we have at the top, if we call this y and then we solve for p, we can use that formula and figure out what will be the probability. But before that, we have to input these values. So for this student, we have negative 4.727 plus 1.3735 times GPA. So GPA, is 4. I can input that as 4. And the next input needed is rank 1. But in this equation, we have rank 2, rank 3, rank 4. We don't have rank 1. So based on the last lecture, when rank 2, 3, and 4 will be set to 0, that automatically means we are talking about rank 1. So we don't have to input 1 anywhere. These 3 become 0. So this is plus 0, plus 0, plus 0. And then the number you get here is your y. So this is the logit value, log p divided by 1 minus p. So if you want to find p, e raised to y, 1 plus e raised to y. Once you find this value, that becomes your probability. That's the probability of this applicant getting admitted. We know that this student is or applicant is like coming from rank 1 school and has perfect GPA of 4. So the chances should be high. So clearly chances are high, 0.68. And if you look at that situation here, 4 and 1, third applicant has those numbers that we used for a new student, and that value is 0.6829. That's what we got. R automatically does all these calculations. We don't have to really do manually. If you look at the interpretation, GPA has a positive slope, 1.137. So that means when GPA increases, log odds of a student getting admitted will also go up. And then you'll notice for rank dummy variable 2, coefficient is negative. And when you go from 2 to 3 and then 3 to 4, that negativeness increases, like negative 0.5, negative 1.1, negative 1.5. So it makes a jump of roughly 0.5 every time, which means as the rank goes down, rank from where these applicants are coming, as that ranking of the schools go down, the odds of that applicants getting admitted also goes down because it's negative. Negative odds means the chances become less and less.
Professor,
Yeah,
can you show us how to predict a single value using R? Or predict
with
for value number two, the 6603.7 rank 3. Can you show us how to do it in R?
this one, right?
No, number two.
In our training data, we had 325. So when you do the prediction, you are doing for all 325. But if you want to do only for one, we can do this. So I'm using same format. So our model is M. Let's say train data. And I want to look at second applicant or second row in the data. Second row, comma, nothing means all columns because we have to provide all columns. Type equals response. That's the probability for second applicant. Coming back to this model, you may also see few other things apart from significant variables. Null deviance. So what is null deviance? It's the response predicted by our logistic regression model without any input variable, only with the intercept. So if you do not include any input variable or GPA or rank, so that's the null deviance. And residual deviance is coming from when your response is predicted by the logistic regression model using the input variables that have been used here. So without the variables is null, and with the variables is residual deviance. So in a way, like you can see, it's coming down. So it has to come down if these variables are really significant. If they are contributing to the model, then residual deviance should come down. One more thing you can do here to understand the model is, so you can make a plot that explains contribution of your independent variables. So there's a function called Termplot. First plot, this is for GPA, and y-axis you have log odds. So how log odds increase as you go from lower to higher GPA values. So you can see it goes up. Make one more hit, then you have it for the rank, the other variable. So you can see the log odds of a student from rank 1 school is the highest, and it keeps going down as we go from rank 1 to 2, 2 to 3, and 3 to 4. This zero line in these plots is when you have p equals 0.5. So the probability of a student getting accepted when it is 0.5, so log odds will be 0 because it becomes log 0.5 divided by 0.5, which is log 1. Log 1 is 0. So this is in a way, it's the midpoint.
So the partial for the variable is actually the log odds.
Yeah, so the idea is that when we talk about GPA, we assume that the only other variable is rank. So the other terms are held constant at their means. So that assumption we have to make, because if other variables are changing, then obviously we cannot talk about one variable. But we assume that the other ones are kept constant at their means. And then you have these values which are basically, you can see it may go from, y-axis may go from negative infinity to positive infinity.
I see. So how about the variance? Does them can split into by variable or in the model level?
Null deviance is when your response is predicted by your logistic regression model that only has the intercept, and we get a residual deviance where the response is predicted by our logistic regression model that includes the independent variables. Like in this case, GPA and rank, when they are included, so residual deviance is based on that. But null deviance is when the model is developed only with the intercept. That's where from you get null deviance.
Okay. The deviance calculation is a probability or is log odds or none of that?
The concept is not same. Obviously, calculations are different, but it is similar to what we do in multiple regression with sum of squares. So it captures the variability in some way, but the formula is not same. It's obviously different. We use a different method here, but the idea or analogy, you can say, we can say that it is similar to sum of squares in multiple linear regression situation.
Okay. It's not some square probability or some square odds, it's something else.
Yeah, it's not sum of squares as it is, or it's not, obviously it's not a probability, because 404 cannot be a probability. Probability is always between 0 and 1. So it's not a probability, it's something similar to sum of squares. Because see, your y values are between 0 and 1. So 0 admitted, 1 is, sorry, 1 is admitted, 0 is not admitted. And the way we estimate these coefficients, we try to find B0 and B1 in such a way that the values for each case, like we have 400 cases. In fact, in training data, we have 325. So for each of the 325 cases, we are, if the response is 1, we should be close to 1. And when the response is 0, we should be close to 0. So this maximum likelihood basically tries to optimize that, and then it gives you estimate that we see here. So the idea is that the model gives us estimates in such a way that in those 325 cases, it goes closer to 1 where actual response is 1, and closer to 0 when actual response is 0. It should not deviate too much. If it is like 1 and the model goes towards 0, obviously it's not a good model. Sometimes, because of the variability in the data, very soon I'm going to show you that it misclassifies. A student who was not accepted, it may say that should be accepted, and student who was accepted, it may say it should not be accepted. And no model actually will give you 100% accuracy. The only thing is we have to find a model that does a decent job. So if I develop a model, it gives me certain level of accuracy, and I develop another model that gives slightly better, so obviously I may tend to go to the other one. Let's go further than these predictions. First, we'll do this for trained data. This is another big difference from multiple linear regression. We don't do this calculation for multiple linear regression. There we look at R square and other things. But here we tend to calculate accuracy, or opposite of that is misclassification. How many times we were wrong. And we will do that using these predictions. If I run this again, and this P1 actually has values like 0.28, 0.299. So basically probabilities. It's not a class. It's not like 0 and 1, the way our response is. To do this calculation, we have to convert these probabilities into their appropriate class. So I will store this in PRED prediction 1, and what I'm going to use is if else, and we'll say if P1 is greater than, so we'll use a cutoff of 0.5. So we'll say if the probability is greater than 0.5, then let's say we admit the student. The value is 1, else 0. So if P1 is more than 0.5, then the value should be 1, otherwise 0. If you run this and look at PRED1 values, I'm going to run PRED1. You'll see that for each applicant, now you have not the probabilities, but zeros and ones, just like what we had in the original data. In training data, admit column is either 0 or 1. Now we can create a table. And in this table, we can use this PRED1. So remember, this is coming from logistic regression model. So this versus the response. Our data is train $admit. So you run that and you get this small table. Let me give a name so that we know which one is actual and which one is predicted, because sometimes there could be confusion. And with this table, there is always a confusion. And the name of this table is confusion matrix. This confusing table is called confusion matrix. And let's call PRED1 as predicted values. Let's call this train $admit as actual values, because they are actual values. You see that the top 0 and 1s are actual, and then these ones in the rows are predicted. What does this confusion matrix mean? How to interpret this? So this is how we'll interpret this. If you look at 208, so 208 applicants were actually not admitted, because 0 means not admitted. And the model also predicted, logistic regression model also correctly predicted. So we have 208 correct predictions for students not getting admitted. And on the diagonal, you have another number, 29. So one means 29 applicants were actually admitted, and the model also correctly predicts they should be admitted. So these are 208 and 29 are correct predictions. So in a way, using these two numbers, you can also get like how often this model is correct or accurate. So if you do 208 plus 29 and then divide it by the total sample in training data, we know that it's 325. So 325 gives you 72.9. So this model is accurate or correct 72.9% of the time. Obviously, the other part is misclassification. If you do 1 minus this, 1 minus this number, 0.27, misclassification error is 27.1 roughly. So I can write down here actually 27.1%. So we can get this misclassification error or accuracy. So different people have different preference. Some people want to look at how accurate it is, and some people prefer looking at the misclassification, how often it misclassifies. If you are looking at misclassification, then 27%. But this is training data. So the model was based on this data, and it is likely to do better with the data that created the model. So the real test of model is with the test data. So I'm going to copy this whole thing and paste it here and make some small modifications. Now we'll do it for test data. And for test data, I also need to do the predictions. Copy and paste P2. Train becomes test. We run, and this becomes P2. That's the matrix for test data. So what is the accuracy of this model with the test data? I have one answer, 70%. Let's do that. So 48 plus 5 are the correct predictions. And then we divide this by 75 because your test data has 75 observations, 70.6 something. And then if you do 1 minus 29.3, for the test data misclassification is slightly higher, but not very far away. The major concern with the building models is that we should not build a model where there's a significant overfitting going on, where the model does very well with the trained data and the test data is totally different performance. But 27.1 and 29.3, I would say they are very close, not a huge difference. This model correctly classifies student or applicants not getting admitted 48 times in the test data and correctly predicts 5 applicants will be accepted and they were actually accepted in the test data. Off diagonal numbers are basically your misclassifications. So this math you can do even that way. 2 plus 20 divided by 75 will give you 29.3. This model misclassifies 2 applicants who were not admitted, but the model predicts they should be admitted. So 2 misclassifications for this, but 20 here. So misclassification is bigger actually here compared to here. Now let's talk about some general things related to prediction, estimation, or modeling. We determine the type of prediction we are doing. We also spend time selecting useful inputs, which is like your independent variables, may be significant, may not be significant. And we try to optimize complexity. If you think in terms of the first one, so we have certain inputs, x1, x2, x3, and so on. And we have a numeric outcome. Outcome is numbers. And a model uses input measurements to estimate the response. This is the response, and this is the input. If you think of people in statistics department versus a computer science department, so sometimes they use same term with the different meaning. And this is one of the situations where it happens. Typically, in machine learning, when your y variable is numeric and you are using some kind of whatever machine learning method, they say that you are doing regression. Now, it is strange that logistic regression doesn't come under this, although we call it like logistic regression. So, in a way, it is a misnomer. Somebody coined a wrong name for logistic regression because of whatever reason. If you think from like machine learning side of people. So, this situation they call classification models, where you have certain input. It doesn't matter whether they are numeric or factor, it doesn't matter. It handles everything or anything. But as long as your y variable, response variable, or dependent variable here is a factor, so we are developing a model that uses input measurements to classify each case. This is a typical classification problem in machine learning terminology. So they have two type of models, one for regression, one for classification. And logistic regression actually falls somewhere here. We do data partitioning, as I mentioned. Nowadays, we have lots of data, and it's always a good practice to partition the data into training and testing. And very often, people not only do like two, but they split data into three. And the reason is when you are developing like a number of models. Let's say model 1, logistic regression, model 2, based on some tree method, decision tree. Model 3 is based on random forest. Model 4 is based on neural networks. Model 5 is based on SVM. So you have like different models. And every time you are using training data to make a model and then test data to test the model, so test data is also getting used very often. So sometimes people keep third data set, which is totally separate from first two. They split data into three. And then once they finalize out of maybe a list of 10, 15 models, you want to use this, then use that third data set and confirm if you are not doing some kind of overfitting. So the data is split, model is fit on training data, and the performance is evaluated on testing data. You have made, let's say, several models. So we create a sequence of models with increasing complexity. Even if you use logistic regression, so there could be a model that includes only one independent variable. There could be a model with 2, 3, and 4. So complexity is increasing as you have more and more variables in the model. Then you look at the performance. So you have several models, you have built several models, and you look at the performance in terms of accuracy or misclassification rate or whatever metric that we have. And you find that this model is 1 star, this model is 2 star, this is 3, this is 3, this is 2. Now the question is which one we should use. There is a tie between third and fourth. So which one should we go for? As far as performance is concerned, both are giving equal performance. Based on whatever, it could be AIC, it could be misclassification, it could be accuracy, based on whatever criteria, both are giving exactly same. So when you say go with the less complex model, what is the thinking behind that?
I mean, generally, less complex models are just easier to explain, right? It's easier to interpret all the parameters as opposed to having more moving parts.
So it may be easier to explain, that could be one reason. But let's say you have like a model with 150 variables and another model with 149 variables. So 150 versus 149, obviously 149 is less complex. But as far as explanation is concerned, 149 also is very complex situation and 150 also is very complex.
You could also be less likely to be overfitting.
Actually, when I say 3 stars for both, that means we have taken care of all that. The background conditions, all those metrics, they perform equally well. Now there's a tie. The only difference is that one is slightly more complex and one is slightly less complex. So the key question is which one we should use. There is a book by Aristotle actually. So he gives some suggestion. I don't know if any one of you have read this book. It's called Metaphysics. And as per Aristotle, the end of theoretical knowledge is truth. End of practical knowledge is action. So sometimes people are looking for truth, explanation, why this, why that. And sometimes, especially like in businesses, people don't go into too much of why this, why that explanation. As long as they see that this is giving me like profit, let's go with this. One explanation I can give from like practical point of view is that if you have less variables, the cost will be less. Cost of applying that model will be less. Now, if you think of cost like 150 variables versus 149, and nowadays storage is very cheap. So storing one extra column on a computer is not going to really increase cost drastically. But what usually increases cost is data collection. If the data has to be collected for that extra variable, you need to use some extra resources. So data collection is still expensive. The net thing is that it could be subjective, but you are right that most often people go with something which is less complex. And things that are less complex are also less expensive. You can reduce cost in some way. That's why it is suggested select the simplest model with the highest validation assessment. So this is a big picture of like what usually happens. If you are thinking in terms of response as or metric as misclassification error or AIC, which you want to reduce when you are selecting between various models, then your training data, you can see as you make it more and more complex, that error is likely to go down, down, down. But with the test data, after some time, it starts to increase. And then out of these two, if they are equal in terms of whatever metric, then go with something that is less complex. Choose simplest optimal model. But Einstein also like cautions us. He says things should be made as simple as possible. So we should strive for that, but not any simpler. So in pursuit of simpleness, we should not like start making it too simple where we ignore many important variables and then the model performance starts to suffer. So some assessment strategies, like when you think of that example of churn, so churn is a case of a decision target. And what is an optimal decision model there? We may want to optimize or select a model by either maximizing accuracy or minimizing misclassification. Some people prefer to work with accuracy, some people prefer to work with misclassification. Now this table that I showed you, so I have made it bigger now, actual versus predicted class. So this entire table is called decision matrix, or a more popular name is confusion matrix. How much the model is confused in predicting a class. This cell here is true negative. If actual class is predicted correctly, where class is 0 and predicted class also is 0, that's a true negative. And predicted and actual class, if both are 1, it is true positive. And then you have false positive, because model says it should be positive or 1, but actually it is 0, so that's a false positive. And then you have false negative. Model says 0, but your actual is 1. So confusion matrix with classification models like logistic regression is a very important assessment tool. With our training data, accuracy and misclassification numbers are given below. So 208 plus 29 divided by the total, you get 72.92. 73 plus 15 divided by the total, you get 27.08. Similarly, for testing data, your accuracy 70.7%, misclassification error 29.3%. So we got this model where we get 70% roughly. So can we say if we have 80% accuracy generally for a classification model, can we conclude that we have a good model? Obviously, like somebody will say 100% accuracy is very good or really good or perfect. But with the real data, we never get 100% accuracy.
It depends what we are predicting.
So like we are predicting whether a student should be admitted or not.
Yeah, if this is the case, I think 80% accuracy is good.
Better than
Again,
chance, no?
Yeah.
What's that? Yeah, the chance of a student getting admitted. Not chance actually. This is the accuracy of the model, which means 80% of the time the model is right. It makes a correct prediction. and 20% of the time it goes wrong. So student should be admitted and it says should not be admitted, or vice versa. So if you look at this confusion matrix once more, I have artificially created two models, model 1, model 2, just for simplicity to understand the point. So in model 1, what is the accuracy? How accurate is model 1?
80%.
So 300 plus 500 divided by the total 1000, so 80%. What about model 2?
Also 80%.
So it's exactly same situation as far as diagonal is concerned. But you see, model 1 is doing misclassification, all of its misclassification here, and model 2 is doing all of its misclassification here. Still, overall accuracy is same, which means that overall accuracy doesn't really help us to look within the model, like these kind of things. We may need a model in some places where it should be more accurate for 1 than 0. We may be more interested in 1, but there may be some application where we are more interested in 0. So if we have a situation where our interest lies mainly in 0, then this model is very bad because it's not doing a good job of predicting or correctly predicting 0, but this model is doing a perfect job of correctly predicting 0. Similarly, this model is not doing a good job of correctly predicting 1, but this model is doing a perfect job or 100% accuracy as far as predicting 1 is concerned. So sometimes looking at accuracy may not be everything. And other important question is, what is the baseline rate? So by baseline rate, I mean what percentage of students in our data set, remember we calculated like a table and we figured out these many students were admitted and not admitted. So what percentage of students were not admitted? Basically, I am running this table and it tells me this is the breakup. So if I do 273 divided by 400, I get 68.25. And 68.25 is the base rate. What I mean by base rate is, forget about everything, forget about logistic regression or any model. Simply reject every applicant. Out of 400 applicants, if you reject everyone, suppose that is your model, that is your baseline model. So you are going to be right 68.25% of the time, correctly predicting students will not be accepted. If you develop a sophisticated model, logistic regression or whatever, and if your accuracy in correctly predicting the outcome is less than this, let's say it is 65%, then there's no point in like wasting your resources or money or anything to build that model. It's worthless because it's less than the baseline. So in that case, if your baseline is less than 80% and you develop a model that is giving you 80% accuracy, that means this model has some potential. It could be useful. But if your baseline in some data set is 90% and your model gives 80%, then you should throw out that model. It's no use. It cannot be used in any meaningful way. We have to ask a question, what is the baseline rate? And then using the confusion matrix, you can do some further math and calculate a term called sensitivity. So how many correct predictions for 1, and then divide that by the total of only that column. So that's called sensitivity. And another term is specificity. So how many correct predictions for class 0, and divide that by the total, and then you get specificity. In our data, run the training table again. This was the table. Sensitivity we will do 29 divided by 29 plus 73, total of that column, which is 0.28%. So this model, which is 73% accurate, the model overall, which is 73% accurate, is accurately predicting class 1 with the accuracy level of only 28%, doing a very poor job as far as sensitivity is concerned, correctly predicting class 1. But what about specificity? So specificity is 208 divided by 208 plus 15. So total of that column, correct predictions divided by total of that column, 93%. So this model somehow is more biased or doing a better job of correctly classifying class 0 than class 1. And it's very clear if you calculate sensitivity and specificity. So accuracy gives you some idea, okay, model may be slightly better or worse, but then you look inside that and you may see that there's a huge variability in correctly classifying a particular class. So that's also something important to look at. Probably can stop here, and I will continue from this point in the next class. I will see you next week.
Thanks, Professor. Good night.
Thank you. Good night.
Thank you. Bye.
Bye-bye. Good night.